Hi, my name's Max, and today I'll be talking to you about section 42.2, double integrals and volume. So let's just jump right into it. Uh, Double integrals is essentially a means to an extension of the iterated integral that was talked about in 14.1, and this is a way to express the volume under a three-dimensional space. So let's say I have this this graph right here of the three-dimensional axis, and I have this shape right here. It's kind of like a curve or a portion of a sphere if you look at it. And suppose I ask you to find the volume underneath this shape, underneath the shape. How would you even approach something like this? It might look a little daunting at first, and which is understandable, but if but let's try to break it down, right? So we know from single variable calculus that we can find the area under a curve, let's say y equals f of x, by approximation. By that I mean we can draw rectangles in the space. Let's try this, this, and like so. We can use these rectangles, irregardless of like width, in order to find the area under the curve. How this works is that these widths, which we will say as d delta x, we can sum the areas of all these smaller rectangles up together as f of x delta x, and these n rectangles together. And what we'll find that as we sum these areas, we'll get a result that's pretty close to the actual area under the curve. So how do we refine this? Well, if we take delta x and make it smaller and smaller, as we take the limit of that as delta x approaches 0, we will approach the actual area under the curve. And that's how we do it for single variable calculus. And in multivariable calculus, or in the three-dimensional space, we follow a very similar concept. But this time, instead of rectangles, we use rectangular prisms. So let me draw this out for you. So instead of this one-dimensional component with delta x, we have this two-dimensional component, these rectangles. And if we cover the space with rectangles, with these rectangular prisms, and we sum these areas up, just like in single variable calculus, we'll eventually get an area that's pretty close, or a volume that's pretty close to the actual volume under this graph. And so how does this work? Well, instead of simply delta x, like in single variable, we have two components. We have delta x, sorry, it should be delta x, and delta y, x and delta y. And the component, or the height of this is z equals f of x, y. And so we can find the volume of this rectangular prism by simply taking the base times height, delta y, times delta x, times f of x, y. And so we'll see here that we can rewrite this delta y delta x as f of x, y, delta a. And now I want you to think about what happens when, just like in single variable calculus, we sum all these rectangles up, or rectangular prisms up, and we sum them so that delta a, so we sum these as delta a approaches 0 as the change in y and the change in x approaches 0 of these n rectangular prisms. Take a limit as delta a approaches 0. Here we would slowly approach the actual volume of the under this curve. under this graph, three-dimensional space. And this is what we represent by the double integral. We double integral of under region R of f of x and y dA, which is dx dy, or dy dx. So the interesting thing to note about this is that dA can either be dx dy or dy dx. The order can be swapped. And how this is significant is that you'll encounter some problems when solving these double integrals where it's preferable to do it in one way, but nearly impossible to do it in the other way. And let me give a breakdown of how like the concept behind this double integral. So say we have this plane here in the space, and we get z equals f of x and y. So how we do this double integral is, let's just say we take the integral from these bounds a and b, and then 0 and f of, or then f, 0 of, like, let's say x of dy dx. Well, we know that from single variable calculus that a and b have to be constant, since the outer bound has to be constants, a and b have to be constants. And so how this works is that we first will integrate this function, the z function, over the xz plane. So we'll get something like this in the cross section. We'll get something like this, just a plane. We're integrating over a plane. And so we'll get something very similar to this two-dimensional area under the curve that we learned in single variable calculus. The difference being that after we find this area, we integrate over this area, we integrate it again over the y-axis. So we would take this area and then kind of just, if you think of it as just filling in the rest of the plane, the shape. We slowly fill it in. Now, this might be a little bit confusing to visualize, so think of it as think of it as kind of flipping the shape over, and you're filling in the base first, where the base is on the xz plane, filling up the base, and then you start filling up more layers until you get to the top and you fill in the entire shape. That's kind of just the principle behind doing these double integrals. All right, so here I have an example to kind of give you an idea of how we use iterated integrals or double integrals to calculate the volume. So we have this plane with the equation 2x plus 3y plus 4z equals 12. Right. And essentially, let me draw this out. We have the intercepts from the x-axis at x equals 6. The intercepts of the y is y equals 4. And the z intercept at z equals 3. So how I would approach this is, first, let's forget about this z-axis, right? Let's just picture this on the xy plane. Let's just picture this equation on the xy plane at z equals 0. So here we can set z equals to 0, and here we can get z equals 0, and we can get the equation 2x plus 3y equals 12, and this is essentially the cross-section at the xy plane when z is equal to 0. And if we were to draw this, you would realize it's basically a line of equation y equals negative 2/3 x plus 4. And it would look a bit like this, where, as we said before, x would intercept at x equals 6, and y would intercept at y equals 4. And so, how we would want to first approach this is we would write the area of this as an iterated integral. If you recall from section 14.2, the outer bound has to be constant values, while the inner bound can have functions. And for now let's rearrange terms to get the equation for z. So we can get z equals 12 minus 3y minus 2x over 4, which would become 3 minus 3/4 y minus 1/2 x. And so this will be our inner function, which we'll write right now. And now we want to consider what we want for dA. So which would be more convenient in this case for the outer and inner bounds? So in some of the examples we'll explore later, you might see that the order would matter, and that in some cases the order is so important that you can't solve it one way, but you can't solve it the other. You can only solve it one way. But in this case, since the intercepts are very well defined and the function is relatively simple, it's just a line, the bounds do not really matter. So let's set the outer bounds as dx dy first. And so since the outer bounds are constant, we see the range of y. So y starts at 0 and goes up to 4. So the outer bounds would be from 0 to 4, dx dy. And the x is a little bit trickier, but what we want to do is we want to solve this equation of the plane, or of the line, in terms of x. So we would get 2x plus, so the equation is 2x plus 3y equals 12. Rearranging and solving for x, we would get x equals 6 minus 3/2 y. And so we would put this here, and since x here's the maximum for x, and then the minimum is going to be x equals 0 for these rectangles here. So we would get x equals 6 minus 3/2 y and 0, end of the function, 3 minus 3/4 y minus 1/2 x dx dy. Let me actually change this to a different color to let you visualize it more clearly. So let's solve the inner integral first. If we're evaluating with respect to x, we can treat y as a constant. So the outer bounds would still be 0 to 4, and the inner bounds, well, we would take the integral of this function, of the z function, with respect to x. So this would become 3x minus 3/4 xy minus 1/4 x squared. And then we would do this from 0 to 6 minus 3/2 y dy. And now this inner function, we can evaluate this by simply just substituting in this for y, this for x, sorry. So let's do that. 3x minus 3/4 xy minus 1/4 x squared would become 3 times 6 minus 3/2 y minus 3/4 6 minus 3/2 y times y minus 1/4 6 minus 3/2 y squared. Let's just evaluate all of this. It's going to be quite messy, but we can persevere. So we get 18 minus 9 over 2y minus 3 times 6 is 18 over 4. And then here we have negative 3/4 times negative 3/2. So we would get plus 9 over 8 y squared. This would be multiplied by y actually. Look at this. And then we would subtract minus 1/4, 36 minus 6 times 3 over 2 times 2 is 18. 18y plus 9/4 y squared. So wow, this is quite the daunting integral, but if we can simplify it, we can see that it's not actually super difficult or challenging in any way. It's just slightly tedious, right? So we would get let's rearrange the y squared term. So 9 over 8y squared. So we have 9 over 8y squared minus 1/4 times 9 over 4 y squared. So we have 9 over 8 y squared minus 9 over 16 y squared. I get 9 over 16 y squared for the y squared component. Next, let's go for the y component, which we would get negative 9/2 y minus 18 over 4y minus or plus 18 over 4y. And we can see here minus 1/4 times negative 18y plus 18 over 4y. And these would cancel nicely, and we just get negative 9 over 2y. And here, and finally we get the constant term of 18 minus 36 times 1/4 equals 18 minus 9, which is just 9. And we have all of our components right here, right here, right here. So all we have to do is to just plug that back into the original integral we have here. Just move over here, and so it will be from 0 to 4 of let's see, of 9 over 16 y squared minus 9 over 2 y and plus 9. So, and now we can solve this integral again to get our final result. So it will become, well, 9 over 16y cubed will become 3 over 16y, or 9 over 16y squared will become 3 over 16y cubed minus 9 over 4y squared plus 9y. And we would evaluate this from 0 to 4. And and let me take you over to this one real quick. So here we didn't have to subtract it from this, because this would evaluate to all this as x equals 0 would evaluate to 0. But you want to look out for this. I would just recommend writing down the full steps of just the upper bound minus the lower bound, plug in 0 for the lower bound, and then evaluate the full way, because you'll never be too sure, right? And so here we have 3 over 16 4 cubed minus 9 over 4 squared plus 9 times 4, and I'll compute the full thing here. Minus 3 over 16 0 cubed minus 9/4 0 squared plus 9 0. And so if we evaluate this, we would get 3 times 4 minus 9 times 4 plus 9 times 4. And we'll just simplify this down. This will cancel out, so it would just be 12.